want this to be precisely defined by all these spaces. So you might have encountered already some different versions of it. All those are very particular case of the things that I'm going to talk about today. So, objective here is to discuss these spaces and some of the subspaces of these spaces. For p between 0 and infinity, we keep on changing the p, so it's pretty important to keep in view that what result is true for what given set of the values of the p. So it's not. So you have to be always careful. In other words, that some of the results are true for particular choice of p, but they are not true for other choice of p. Always take care of the thing that which result is true for which value. Okay, so p value number between 0 to infinity, and let's take f to be a real value, maybe a complex value, a measurable map. Define by LP norm. It's basically the LP norm of it. How do you define it? That you integrate over x. By x, I mean, measure space basically. P to the power of f will expect to measure mu, and mu can be any measure actually, and that's what makes all this powerful actually. That what you are defining here, you can take any measurable space and you can define LP space corresponding to it. And the P2 okay? So that's the definition of LP. So what I mean by the LP space, LP is denoted by mu. So usually, for example, when you write L to AB, so you kind of encounter this kind of a thing. By L to B.
The measurable one interval.
So it's a class of square integrable functions, okay? But they are square integrable with respect to the Lebesgue measure. Okay, so here I'm putting a measure actually, but here I'm putting an interval. Okay, but if I take Lebesgue measure, okay, that we define previously, and you consider this particular interval, and you can say that basically this is the Lebesgue measure. So L2 of Lebesgue measure is restricted to this bar. So I can take, for example, probability measure. My probability measure is going to be, so it's going to be the square integrable functions, space of the random variables, for which the second moment of the random variable is finite. Absolute of the second. So in other words, what you are defining is a pretty abstract thing. So by giving it a name LPP, we take any measured spacing corresponding to it you can define in LP space. So LP is the collection of the functions, such kind of functions, which are measurable. Okay. Measurable. And the LP norm that we have defined of F is finite. Okay, that's what is the definition of. Now, one of the key things that basically you can see it so actually that factoring of this f, which we usually treat f, is not just an f, it's not a function, but it's a class of function. Okay? It's a class of function. So I'll define an equivalence relation, and I'll show that every element in these spaces basically not just a function but a class of a function. Why is it the case? Now, by the way, when the LP norm of f is going to be 0,
F is equal. Yep. So must have been
yes, so we need to say precisely that f is 0 almost every time. Because the diagonal is 0, is 0, this is 0, if this is 0, then
the result we have.
the must be the integrand must be 0 almost every, and hence you can say that f is almost every. Let me define the equivalence relation. Let's say that f in this space LP is equivalent to G. Okay. If f is equal to G almost everywhere. So what do I mean by that? So in other words, f is equivalent to G if f is equal to G on almost all part of the space, and the part where they don't agree
Is
is measure 0. Okay? You can easily show that f is like this relation is an equivalence relation on this space. Right? The trouble with this, why need this equivalence relationship? Think about it. Because you can have functions which are not 0, but they're okay. You can have function whose norm is 0, but they are not necessarily 0 everywhere. Just think about it. This is 0. In order to turn it into a norm, so what's the definition of a norm actually? So the first condition to turn it really into a norm. At the moment I can't say this is norm. So to turn it into a norm, what you have to show that if the norm of something is 0, then that thing must be 0. Without exception, not almost everywhere and so on and so forth. Are you getting the point? But the trouble here is that if this is 0, then f is not entirely necessarily 0. It can be 0, but almost everywhere. In other words, there can be points in the space where this is not 0. So in other words, a non-zero function can have a non-equal to 0. So how to solve this problem? I mean, even the first condition is not satisfying. So what we are doing, we kind of defined an equivalence relation, which is doing what? It's taking all those functions, okay, whose norm is 0 into one bucket actually, so that you can identify all those functions whose norm is 0, and you can identify them as a single function actually. Now think about it. So if f is equivalent to g, and f is related to g if and only if f equal to g almost everywhere. Okay. Now I'm saying that all those functions, okay, which are equal to 0 almost everywhere, they will all be in one class actually. And that class would be what? Class actually. Okay? And whose norm is 0. So that problem goes away actually. That problem goes away. Because if you don't do it, this guy is not even normal. Okay? So the norm is a trouble.
So sir, the set LP will be set of losses.
Yes, yes. That's what it is. Essentially that you in LP space, every square integrable function, P integrable function is basically a class of functions. Okay? So in other words, advantage of defining this relation is that now your norm is well defined. Now it satisfies the first condition. Okay? The rest of the condition, we have proved different kind of inequalities should tell us. Prove it. For example, why the triangle inequality would be true here? Because you have something called the Minkowski inequality. What does Minkowski inequality say? That if you have a pth norm of a sum, and that is less than or equal to the sum of the pth norms of the functions actually. Okay. So that's what the Minkowski inequality tells you. Okay. So since we have kind of did this in functional analysis as well, okay, particular case for similar kinds of argument, we can use and we can show that basically this is a norm actually. But the real clinch was here that you can have multiple functions whose norm is 0, but they are not necessarily 0 everywhere. So what you are doing by defining such kind of a equivalence relation, you are taking all those functions which are almost everywhere equal to 0, you are putting them in a one class, and that is 0 class actually. Okay? And hence you can now say that there is only one vector in LP space that has 0 norm, and that is this 0 class actually. Okay? Is it making sense? Now, this definition is valid, all this is true when P is between 0 to infinity. So finite and it's positive. P equal to infinity. Is P equal to infinity. Okay? In other words, what would be the meaning of L infinity? I mean, we have already seen it. I mean, do you remember, for example, from your real analysis course, that what is the meaning of L infinity in R, for example?
Supremum norm.
Supremum norm.
Was finite.
It's a collection of roughly the bounded sequence.
Bounded sequence.
A collection of bounded sequences. Okay. And similarly, you're going to have something similar. So, for P equal to infinity, let me first define a function f. Okay. F is essentially bounded. Essentially bounded. Okay. If we can find a non-negative finite number, okay, such that this function, so the function are bounded by this number almost everywhere. So it's kind of a weaker motion than boundedness actually. Okay, so this is a weaker motion than boundedness. Boundedness are essentially bounded, but essentially bounded are not necessarily bounded actually. Because for boundedness we need to have this true for all x actually. But here you're saying that okay, it's true for almost all x, but for the points where it is not true as a measure. So you call such kind of functions as essentially bounded. Okay? And at infinity of mu, okay? So at infinity of mu is a collection of such kind of functions. So it's a collection of functions such that f essentially is bounded. Okay? I will put this term in the kind of a singular statement that it's a kind of a collection of the maps that are measurable, and this measurability is always there, such that the infinity norm of f is only that. Okay? So I'll write this mathematically here. But what do I mean by infinity norm of f actually? Because there are different notions for it. So the infinity norm of this is something that you sometimes denote essential suprema. It's not suprema, but essential suprema.
Unknown termination.
Of f of x, I'll define it more precisely. Okay. That's in the next section. And what do I mean by essential suprema? By essential suprema, I mean the infimum of m's, okay, such that f of x is less than or equal to m almost. Okay. That's what is essential suprema. So you can have many numbers which are somehow kind of bounding the function almost everywhere. The smallest of all. Okay? And such a smallest of all, you can also call it essential supremum. Give it a name. An infinity form. Is it making sense? I'll do some examples. Here's a small proposition. So if f, so are we happy with it actually? Are we happy with it? So, it's a vector space, we have a norm on it, so it becomes a normed space. Okay. And the norm is defined in terms of the essential supremum. Which becomes basically, if you have a sequence, if you have sequences, then it becomes supremum of the sequence. For example, L infinity is smaller than L infinity. Okay. So what you are defining is generalizing your own previous function. And you're doing it for any measure. So this is something beautiful. If you have a measure space, you can take it and create a LP space. Okay. So if F is essentially bounded, so usually when people talk about elements of L infinity space, they call it bounded actually, but be very careful that. Okay, when we say bounded, we mean essentially bounded. But obviously, all bounded functions are here. So if f is in L infinity, then all values of x, f of x can be bounded by the f L infinity norm of f actually. Almost every. It was too quick. Okay. Almost every. Then it's even more natural actually. So almost every. There's a proof. if this guy is infimum of such m's which satisfy these conditions, then obviously I can find a sequence of such m's, okay, that converge to this infimum. Okay, which converge to this infimum. So in other words, you can always approximate infimum and supremums by the elements of the set, whatever the set you have actually. So if this guy is infimum of the m, in other words, I can find some m's here which can approximate this norm. Okay? And obviously these norms are since from this set, so it must satisfy this condition. Okay? So there exists a sequence mk such that it approximates this and f of x, all of these f of x are less than mk, less than or equal to mk, almost everything. It satisfies this condition. By the way, I can write this guy more precisely in the sense that for, and hence what else follows from here is that for each k, I can find an nk, I can find a set nk, measurable set nk, such that, okay, such that measure of nk is 0 and f of x is less than or equal to mk for all x in nk complement. So basically what you are saying is just writing the same thing but in another language. So for each such mk, in other words, each term in this sequence I can find a set actually. Okay, a null set whose measure is 0, and outside that null set the inequality is satisfied.
That's from where it follows.
I'm sorry.
From where it follows.
So it follows from definition. So I'm asking from what does it mean? What is the meaning of this expression? So it means that if I say that this is less than mk almost everywhere, this means that the set for which this is not true, okay, has a measure 0. So I'm saying, okay, for each k I can find an mk whose measure is 0, okay, and outside that mk this inequality is satisfied, and hence inside the mk the inequality is not satisfied. Okay. Now, since we have lots and lots of of what we call k's here, so at least as much as the natural numbers you have. So let's put all these nk's into a set. Give it a name, k equal to 1 to infinity. Okay? So just combine all these sets. And we are almost done. Then what would be mu of n by the way? So it must be 0. Okay. It must be 0. Because mu of n is equal to mu of the union, and the union is less than or equal to the sum of the measures. You have 0, so you get equal to 0. Okay. And for each x in n complement, okay, so for each x in n complement, since what is true? By the way, n complement is going to be what? Is going to be the intersection I equal to or k equal to 1 to infinity and k complement. So that's for each x, it's in all of these n. So it's like a this and this condition are satisfied. Okay? So I can say for each x in n, for each x in n, we have f of x less than or equal to mk. Do we agree with it? Because if x is in, mk complement, so this condition must be satisfied, and okay, this is obviously given to me that mk is something that this way. Still, you have it. In other words, these two things are not only true for each mk complement, but it's also true for the intersection of these complements. So I can say simply that now you have what thus say finally that this f of x is basically less than f. Why this would be the case?